So I have a couple of options about how I do the order of topics in this class. And I've decided that this year we're going to start with some physics topics. And here's the reason why. In the last unit, we talked about the scientific method and what is science and how do we go about doing science. And the first thing that we do is we ask a question. And then we come up with a possible answer to that question, like a hypothesis, and then we test our hypothesis. So that has been the order of science ever since people have been trying to answer questions, right, about what they see and how it works and whatever it might be. So if we talk about the quote-unquote birth of science, and whether you say that that's ancient Chinese astronomers or ancient Greek philosophers or whatever we consider to be the start of science, it always starts with a question. And we ask questions based on things that we see. We ask questions based on our observations. And the first thing that these ancient scientists could see was motion, the motion of things here on Earth. And so they start asking questions about, okay, well, what's going on with this motion? How does it work? How does it relate to other things? And those are the first quote-unquote questions that we ask. So that field of science is the basis of our further study. We'll find out that as we introduce these concepts here, they will carry us through basically the entire course. So we're going to start off with a branch of physics called mechanics, and that deals with the study of motion, like it says. And one thing that's consistent with mechanics is that when we are trying to describe the motion of an object, we're trying to answer questions, but 4 specific questions. So the first thing that we want to know about an object to describe its motion is, where is that object? The second thing that we want to know about that object is, what is it doing now? The third thing would be, well, what is it going to do in the future? Is it changing what it's doing? And then the fourth thing is, when? When do all these things happen in relation to the other answers to questions we may have found? So when we are studying mechanics, when we are trying to answer questions about the motion of an object, if we can answer those 4 questions, where, what next, and when, we'll do a good job of describing that motion. Seems like a logical place to start with the first question, where is the object? And hopefully you're not too surprised to find out that the answer to that question is called the position. So we define the position of an object as the separation between an object and some reference point. So we're going to base our discussion today on this lizard. So here is a lizard sitting on a bunch of rocks. And you might think that the lizard is cool and you maybe want to tell other people about it or whatever it is, but the first question we're trying to answer is, where is that lizard? You could say, well, it's sitting on a bunch of rocks, but that doesn't provide a whole lot of context. Anybody who's not right next to you is really not going to have any idea about where that lizard is. So when we are describing the answers to those 4 questions about mechanics, we need some context. Now, depending on how detailed you want to get, that context can be more and more complex. But we're going to start off simple. So here, same lizard, same rocks, but I laid a ruler down next to these rocks. Now, that ruler does not distinguish these rocks from any other rocks in the world, but it does at least give us a little bit of context in order to describe the location of the lizard, at least in relation to the edge of the rock. So I take my ruler and I line up the 0 mark of the ruler right with the very far left edge of the rock. And now I have at least a little bit of context to describe where that lizard is. And so if we use the middle of his body, let's call it, I don't know, here-ish. Okay? So now we can describe the location of that lizard, at least in relation to the far edge of the rock. It might not do a good job of describing its overall location, but it's a start. The whole idea of having some context in order to accurately answer those questions or describe the answers to those questions to somebody else, we refer to as a frame of reference. We also refer to that as a coordinate system. Those two terms are interchangeable. They mean the same thing. And as you can see, the definition of frame of reference is the context in which we study motion. And when we look at further describing the frame of reference, we need two things: a reference point and a directional system. So going back to the picture of our lizard sitting on a rock, by laying the ruler lined up with the far left edge of the rock, we have made this our reference point. And we're going to call that reference point, at least in terms of this context with this ruler, 0. So we're going to call the far left edge of the rock the 0 point. And then we can describe where that lizard is in relation to the 0 point. Now, even though it doesn't show it, there is a possibility that some of the rock, or maybe it's a stick or something, exists over to the left of the 0 point. So it's possible, even though it doesn't show it in this picture, that this lizard could be on either side of the 0 point, depending on where we put it. Now, we can eliminate some of those possibilities with careful placement of our reference point, but it is possible that things could exist on either side. And that's why, when we are describing or determining our frame of reference, not only do we need a reference point, where are we going to make all of our measurements from, but we're also going to need some kind of directional system to make sure that everybody's on the same page. So, in this case here, we can describe the location of this gecko as, let's say, 24 centimeters away from the reference point. Now, you may think to yourself, wait a minute. There's a lot of places that could be 24 centimeters from the edge of that ruler, which we have deemed our reference point. And that's true. So one thing that we do when we're starting off our study of motion, when we're introducing mechanics, is we limit the possibilities. And that's what we're going to do here to start off in this little section. We are going to limit our possibilities to one dimension. You may have heard of three-dimensional motion or three-dimensional whatever, right? One dimension is the simplest as we can get. One dimension is basically a straight line. And on a straight line, the number of options we have for locations is limited. We can either be to the left or we can be to the right. And so, with that being said, when we talk about our directional systems, we only have to distinguish left from right. Now, you may realize in your head, well, I can't use left and right because depending on what side of the rock I'm on, I could describe the lizard to the left of the reference point or the right of the reference point, depending on where I'm standing. And so one of the ways we do this is, instead of saying left or right, we imagine this ruler as part of a number line. Hopefully we remember number lines from math class, right? Number lines have a 0 right in the beginning, but then they have numbers extending in both directions. We distinguish those two directions with a positive sign or a negative sign. So in one dimension, there's only two options. And we distinguish those two options as positive or negative. So the way that our ruler is labeled in this picture, I'm going to assume that those 10s, 20s, 30s, and 40s that are labeled are on the positive side of 0. So to describe the position of this lizard, not only would I have to describe how far away from the reference point it is, I also have to describe which direction from the reference point it is. So in this case here, I could call the position of this lizard positive 24 centimeters. Again, if you don't know where this rock is in relation to anything else, like what room it's in, or what building it's in, or what city it's in, saying that the position of the lizard is positive 24 centimeters doesn't really do you a whole lot of good. But the point here is that we start adding some context to our description so we can make the description a little bit more detailed. Okay? So, to sum up, position describes where that object is in relation to some reference point, but then also we have to describe which way are we going from that reference point in order to accurately describe its position. And at least for starters, we're going to limit our options by containing our motion to one dimension. So, position. Where is the object relative to a reference point? Which direction from the reference point? That's the answer to the first question, where is the object? All right? Now, that's great until this happens. Our lizard has decided he doesn't like the position that he's in, so he takes a little stroll to the right. Okay, well, we have to describe that as well. So what happens when the lizard moves? Well, it depends on how much we want to describe. So the first description of movement we call displacement. And displacement is described as the change in position relative to the reference point. Now, hopefully you remember from math class, and if you don't, I'm going to describe it to you now. Change in position. If we want to describe the change in anything, we need to know two things. We need to know where does that object, or what condition does this thing end up in, compared to what was it like at the beginning of the situation. So when we're talking about the change in something, we can calculate it mathematically by looking at final minus initial. What condition does it end up in versus what condition did it begin in? And we have a mathematical symbol that represents this operation, and it looks like a triangle. The triangle is actually a Greek letter. It's a Greek letter delta. And whenever we see delta, it means that we want to compare the final condition versus the initial condition, or the change in whatever it is that we're trying to look at. So in this case, when we're looking at displacement, change in position relative to a reference point, we symbolize that with the notation delta x. Delta x. Delta meaning change, and x meaning position. Because remember, right, our frame of reference is a number line. And generally speaking in math class, we call the horizontal number line the x-axis. So if we want to know the change in position along the x-axis, we can represent that with the notation delta x. And in order to find the change in position, we need to know where on the x-axis does it end up versus where on the x-axis did it begin. So mathematically, we can describe displacement with this equation. All right? So, looking at our lizard, all right? Notice I've added back my context, right? My frame of reference, the ruler, and it shows where the lizard started versus where the lizard ended up. So, the change in that position we represent as delta x, the change along the x-axis. And we just learned that if we want to calculate delta x, we can take a look at where does that lizard end up, the final position, minus where does that lizard begin, the initial position. So we take a look here, and if we take a look at our ruler, right, here's the final position of the lizard, at least in the middle-ish somewhere, right? And so we can signify or describe that as 85, I don't know if it's meters or centimeters, let's call it centimeters, most likely, okay? But remember, when we're talking about frame of reference, we need a reference point, but we also need a directional system. And we've called this direction our positive direction. So this lizard ends up 85 centimeters from the reference point, but on the positive side of x. Or sorry, positive side of 0. So the final position is positive 85 centimeters. Minus, where did this lizard start? Well, here it is, okay? I'm going to call that positive 24. So we can take a look at where the lizard started versus where the lizard ended and find out that that lizard, we do a little bit of math, and we find out that that lizard moved 61 centimeters. Okay? So the displacement, the change in the position, is 61 centimeters. And that's great. But we're looking at the lizard a little bit later on, and we see this happen. Lizard moves. We want to describe his motion. And so again, we can use displacement. So throw some context on there. Here's my reference point. I said this direction is the positive direction. And this would represent the change in the lizard's position, or the displacement. And we learned previously that delta x is equal to x final minus x initial. Where does the lizard end up compared to where the lizard started? So we plug in a couple values. Here's the initial position of the lizard. I'm going to call that positive 78 centimeters. Oh, sorry, my bad. Hold on. Got to do the final position first. So this lizard ends up here, let's call that positive 14 centimeters, right? And comparing that to his starting point, positive 78 centimeters. So we do our math here, right? And we end up with a negative 64 centimeters. Okay? So, two things that are different about this displacement than this displacement. One, the value's bigger, 64 versus 61, but maybe more importantly for our discussion here, when we plug in the numbers that we get, or from our measurements of where it starts and where it ends, this one ends up as a negative value, and this one ends up as a positive value. And that's all right. Because displacement is describing the change in position. But we said on a straight line, that change in position can occur in two ways. It can occur, going this way, right, to the right as you are looking at it right now, or it can occur in this direction, to the left, as you are looking at it right now. But we've said left and right isn't good, right? We can't do that. Because depending on where we stand, that changes. But we said that if we go back to one dimension, we can distinguish the two directions with a positive and a negative. So here, displacement, even though I didn't actually write it down, I probably should, comes out to be a positive 61 centimeters. Here it comes out to be a negative 64 centimeters. Displacement is our first example of something that we call a vector quantity. Vector quantities tell us two things. They tell us magnitude and direction. Magnitude is a fancy way of saying how much. Direction tells us which way. So, looking at the two trips of our gecko, here we calculated his displacement to be positive 61 centimeters. Here we calculated his displacement to be negative 64 centimeters. The positive and the negative tell us the direction. Which way did the displacement occur? The number tells us the magnitude. How big of a displacement was it? Or how far did the gecko go? Now, just because this is a negative number, right, doesn't mean it's small. You have that sort of in your mind from math class. But here, the positive and negative are not telling us anything about how big something is, only which direction. The bottom displacement is actually a bigger displacement. 64 centimeters is bigger than 61 centimeters. The negative is only telling us that that 64 centimeters was back towards the left, at least the way that we're watching it here, whereas the positive sign tells us that the 61 centimeters was to the right. So, displacement, vector quantity. It has to tell us magnitude and direction. How far did the lizard move, but also which way did the lizard move? So, that's one way of describing where is an object, at least in terms of where did it start versus where did it finish. But sometimes that always doesn't do us justice. It doesn't actually describe what happened during the trip. Displacement only tells us the change in position. And when we're calculating it, we only take into account where does something end up versus where does it start. The whole middle part of the trip is totally disregarded. And sometimes we need that. And so in order to describe the middle part of this trip, we use the term distance traveled. Distance traveled is the length of the total trip. Doesn't matter which way we go. Positive and negative are not important when we're talking about distance traveled. We're only dealing with the length. And as a result, distance is a different kind of measurement that we call a scalar measurement. Scalar measurements only indicate magnitude. They only tell us the length of the path, but not which way it went. Example, if you've ever looked at the dashboard of a car before, underneath the speedometer is something called the odometer. It tracks the mileage of the car. One thing it does not track for you is which direction those miles were driven. Because if you're talking about using it for maintenance purposes, which way the car is driven is not important. It just is how far the car has gone. So, when we talk about certain types of measurements, sometimes the direction is important. Like when we're describing these two trips of the gecko or the lizard. But sometimes we only want to know how far that lizard goes. It doesn't matter which way. Or how far the car goes. It doesn't matter which way. So, we've introduced 5 terms so far. All right? First, position. Where is an object? In order to answer that question, we have to have some context, and we call that context the frame of reference. And to get the frame of reference, we need a reference point and a directional system. 2, we have talked about the displacement of an object. What is the change in its position? Where did it start versus where does it end? And displacement is an example of something that we call a vector quantity. Vector quantities tell us magnitude and direction. How much and which way. Because sometimes that's important when we're describing motion. But sometimes it's not. And so when it's not important, all we describe is the distance traveled, the length of the total trip. How much total distance did we travel from where we started to where we eventually end up? Distance traveled is an example of a scalar quantity. A scalar quantity only indicates magnitude. It only tells us the length of a path or how much of something there is, but not which way. Right? So, those are the terms we've introduced today. Remember, what we're doing here to begin is studying motion. And we call that study of motion mechanics. And when we are describing the motion of an object, we're looking to answer these 4 questions. Where is the object? What is it doing now? What will it do next? And when are all these things happening? So today, we spent time talking about the where question. Starting on Monday, we will start talking about the what and the what next. Enjoy your weekend, everybody, and I will see you guys on Monday. Don't forget, take a look at Google Classroom. There is a little bit of a homework assignment, it's just some reading. And if you haven't submitted your biggest bubble project lab report, please make sure you do so ASAP.